All right, well, welcome to the second part of class 3, which will deal with simple regression. So class 3, part 2, simple regression. The first part of class 3 dealt with correlation, and now we're going to go into the second part, which will be simple regression. So simple regression relies upon the linear model. Obvious question, what is the linear model? So what is it? What is the linear model? Well, the linear model is a simple way of predicting the value of one variable from another. So it's a hypothetical model of the relationship between two variables. The model used is a linear one, a straight line one. Therefore, we describe the relationship using the equation for the straight line, which you probably learned back in grade school at some point. And I would add here, so the red notes are now my notes. So Field says it's a way of predicting the value of one variable from another, which is true. But we should add that we also often use regression for prediction, of course, but also theory testing and understanding. And of course, it's not in the prediction that the problems emerge. It's really in the theory testing and the understanding that the additional problems or issues do emerge. Okay, so again, we said with regression, we're using a straight line. We're describing using a straight line. So here's the equation. And this would be, now this is the equation for the actual data. So, or the actual observations. So we have an observation I, which could be observation 1, observation 2. I corresponds to the number of subjects or participants. We have an observation on our y variable, and that's going to be equal to, in parentheses, a b weight, a b sub 0, plus a b sub 1, another b weight, or actually the first b weight. This is going to be a constant, as we'll see. A b weight times our x value for that subject. If I is 1, then it would be the x value for the first subject, plus an error term for that subject. Now, of course, if we were looking at the actual prediction, would now have y predicted, which is often y hat, would simply equal the b sub 0, the b weight for the constant, or the constant, plus b sub 1 times x sub I. That would be the equation. Now, when we look at this equation again, y is the observed y value, x is the observed x value. Again, this is the equation for the actual observed data. Once we get this, then we can use it to predict the y's. Our e, again, is our error term. This b0 here is the intercept. Now, I don't like that Field here wrote it with a big B, because I think you should restrict big B's to betas or standardized values. So I don't like seeing the big B there. I like to distinguish between big B and little b's. But of course, since it's the constant, if we had the standardized equation, the constant wouldn't even be in there anyway. But so this b sub 0 is the intercept, the value of y when x equals 0. It's the point at which the regression line crosses the y-axis, the ordinate. And we usually call this the constant. So the constant is this b sub 0 value, the constant in the equation. If we are using standardized data, or if we are using big B betas, this will drop out. Now, a little tricky thing here, there is a way to make a regression go through a 0 even when you're not dealing with standardized data, but that's pretty rare, and we're not going to deal with it. Okay, then this next b sub 1, or b sub I, although again, I think it should probably really be written b sub 1 right here, is the coefficient for the predictor. It's the gradient or slope of the line. So it's the slope of the line. It's the direction or strength of the relationship. So if it's negative, the relationship between x and y, as x increases, y decreases. If it's positive, as x increases, y increases. All right? Of course, we can have different intercepts and different gradients. So field is just showing you here's three lines, three regression lines that would all have the same intercept but different slopes. Here's three regression lines that would all have the same slope but different intercepts. All right, so now field gives you a musical example. A record company boss was interested in predicting album sales from advertising. So you see we have one dependent variable, I hope you realize, which is going to be album sales. And then we're going to have one predictor variable, advertising. So one y variable, album sales, one x variable, advertising. So there's 200 different album releases. That's our data. Note again, our data, of course, doesn't have to be people. Here it's going to be album releases. In the example, the COVID data, it's states. But again, usually, of course, it would be people. And so our outcome variable is going to be sales, CDs, and downloads in the week after the release. So a record company was interested in predicting album sales from advertising. Again, data 200 different album releases, outcome variable is sales. The predictor variable is the amount spent promoting the album before its release, the number of plays on the radio, and the image of the band. Of course, in this case, we're only doing a single variable regression, simple regression. So we're only going to be using one of the predictor variables. So here we have a scatter plot. It's probably one of the first things you want to do, produce a scatter plot. It's a scatter plot showing the relationship between album sales and the amount spent promoting the album. So the x-axis is advertising budget in thousands of pounds. The album sales are in thousands. They're the y-axis. Here you can see the intercept or constant and the regression line. And it's linear, and r squared is 0.335, it tells us. Of course, this is our scatter plot of data. The tricky part, though, and of course in regression is, when we're looking at those lines, in the early years, sometimes people just tried to actually draw a physical line through the data. If you go back studies in the 50s, 60s, even some in the 70s, people would actually try to just draw a line through the data. However, it's called regression because scores actually regress toward the mean. Or another way of saying that, if we know nothing about the situation, given our best solution is to minimize or have least squared errors, we should predict the mean. So if there's zero correlation between two variables, we should just predict for everybody the mean of y. That will minimize least squared errors. And that's partially because that's what we're defining as the best solution. We're defining the best solution as that solution that minimizes least squared errors. So if we knew nothing, we would predict the mean. However, you shouldn't reify that. Okay, we don't want to reify that movement to the mean. It does not mean that scores somehow magically run downhill toward the mean. It does mean, for example, though, if we take a parent with an above average IQ, we would actually predict that their child would have an IQ that's above average, but lower than the parent. And that's because predicted scores regress to the mean. That doesn't mean that over time IQ scores are regressing to the mean, because they're not. IQ scores are pretty much staying stable or maybe even increasing over time. But it's because of the phenomena that to minimize least squared errors, when we don't have information, we're going to predict the mean. Now, this whole idea of regression to the mean leads to a lot of different paradoxes. It gets very tricky when we add in that our x variable is not perfectly reliable, that our x variable probably doesn't have perfect construct validity. So the interpreting this regression paradox that occurs because scores are regressing to the mean gets a little tricky. It's an advanced topic. We're not going to cover it here in this class. When I teach personnel selection, I usually go over it. Sometimes in tests and measures, I go over it a little, but it's a tricky topic, one beyond this course. Okay, so anyway, beta or B values. B1 would be the coefficient for variable 1. V2, the coefficient for variable 2, or X, these would be X. So B1 would be the coefficient for X1. B2 would be the coefficient for X2. And Bn would be the coefficient for Bx, B sub X. Of course, again, we're in this case only dealing with simple regression. Okay, estimation. We're using the method of least squares, which means we want to minimize the total error across all subjects between their observed scores and their predicted scores squared. So to get total error, we take each observed value, we subtract from it what the model would predict, we square it, and then we sum it from the first subject to the last subject, or across all subjects, and that gives us our total error. And of course, what we want to do in regression is minimize this least squared errors. So we want to minimize this least squared errors. That's hard to say. The fit of the model. The fit of the model is based on the data, but of course, the model may not always perfectly reflect reality. In fact, it rarely does. And actually, in engineering, you might have almost perfect fits. But when you're dealing with people, your fit is usually going to be pretty poor. But we need some way of testing how well the model fits the observed data. We usually use either an F test. You're probably familiar with the F test from ANOVA last semester, or an R squared measure, which is simply really the overall correlation between the overall correlation for all of the data, if that makes sense, squared. But again, in this case, we're just dealing with one variable, so it's a simple regression. So Field gives this, which is a good way of describing it, except I don't like his labels. You know, again, I said in, I think, the first lecture, sometimes authors will use things different than most other people. This is where Field does it, and I find it a little confusing. But so he shows you there's three sums of squares. There's sum of squares total, which uses the differences between the observed data and the mean value of y. There's sum of squares R, he calls it, which uses the difference between the observed data and the model. So here's the model, here's the observed data. SSR, SS sub R would be these differences. SS sub T would be these differences. And then SSM, which is the differences between the mean values of Y and the model itself. So this is SSM is the differences between the mean value of Y and the model itself. So in summary, SST is total variability, or variability between the squares and the mean. SSR is residual or error variability, variability between the model and the actual data. Now, a lot of people, because that, might call that SSE or SS error. And then there's model variability, or SSM, which is difference in variability between the model and the mean. Now, again, I would say SSR, a lot of times you're going to see instead as SSE or ESS, and that would be your sum of squares error or your error sum of squares term. And then a lot of times you're going to see SSM called SSR for SS regression. So the sum of squares due to regression. So that's where it gets confusing. He's saying SSR, which a lot of people might think is SS regression, but he's using the R there to mean residual or error variability. So he's right because he's defining these things, but it could be easy to get confused. So you have to keep in mind how he's defining these terms. So then we can move on and look at the F statistic, or testing the fit, the F statistic. And this is going to be very similar to what we do in analysis of variance. So SST, or the total variance in the data, is going to, of course, be made up of SSR, or error in the model, and SSM, or improvement due to the model. And if the model results in better prediction than using the mean, then we're going to expect that SSM would be large and much larger than SSR. So our model fit is going to be, how does SSM compared to SSR? And SSM and SSR make up SST, or the total variance in the data. Now, when we actually do this, we get an F statistic. The F statistic is not based on sum of squares, but mean squares. The sum of squares are total values. Mean squares are expressed as then averages. And then to get the F value, the F statistic, and again, I hope you remember the F statistic from analysis of variance. To get the F statistic, it's simply mean square for the model divided by mean square error, or residual, or he's calling it R again. But it's really sort of mean squared error. And then we can also get R squared. R squared is the proportion of variance accounted for by the regression model. It's actually the Pearson correlation coefficient squared. So if we get sort of the, in this case, a single variable model, it's simply going to be the Pearson correlation coefficient squared, would be R squared. And of course, we can get the correlation coefficient, or R, by just taking the square root of that. R squared is also going to be equal to the sum of squares sub m divided by the sum of squares sub t, or the sum of squares model divided by the sum of squares total will give us our R squared, which is interesting. We can also determine whether individual B's are significant. We use a t-test. The t-test to determine whether an individual beta weight is significant is simply B observed minus B expected over the standard error of B. Of course, we know that in most cases, unless we're getting really fancy, B expected is going to be 0. In most cases, we're hypothesizing our B expected is going to be 0. So if you remember your math again from grade school, a number minus 0 is simply the number. So B observed minus 0 is B observed. So our T is going to be equal to B observed over the standard error of B. And that's going to give us our significance test for our individual predictors. Anyway, moving on here. And Field gives you these nice little charts. Again, you can see he suggests we do our initial checks, linearity and unusual cases. If there's a lack of linearity, consider transforming the data, running initial diagnoses or your initial regression, and save your diagnostics. Check your residuals for things like linearity, homoscedasticity, independence, and normality. And independence. You can do that by graphing your Z predicted versus your Z residual, which is just your Z value for your predicted scores versus your Z value for your residuals or errors. You can look at normality of the residuals. You can use graphing them using a histogram, and of course, normality of your data. If your assumptions are met and there's no bias, then you would say the model can be generalized. Of course, we don't know generalized to what. I really think that probably means we can have faith in the internal validity of the statistical results. So I would probably change that to we can have faith in the internal validity of the statistical results. We don't really know whether the results can be generalized in the sense of having external validity. But we know that they have internal validity at least. We can trust the statistical results. What external situations they might generalize to is somewhat unknown. Again, he suggests checking heteroskedasticity. Well, I'm sorry, he's saying after you check, and if there is heteroskedasticity, then you could either run weighted least squares regression, or you could bootstrap your confidence intervals. If there's no normality, also you can bootstrap confidence intervals or transform data. If there's a lack of independence, you can use a multi-level model. Now, in this course, we don't get as far as multi-level models, but multi-level models are important. We just don't get that far. So we can sort of leave that off. Your data at this point, you could just say your data better be independent. Okay, so in terms of assumptions, variable type, the outcome variable must be continuous. Again, a continuous variable means it can take on a range of values. It's debatable whether, for example, a Likert scale 1, 2, 3, 4, 5 might be continuous, but you could probably regard it as continuous. I will say it's not necessarily true that it has to be continuous. Dichotomous data is always interval data. So technically you can run a regression on a dependent variable that's dichotomous. You probably shouldn't, because you probably should be running logistic regression in that case. But we could get into a debate here. Technically, you probably can run regression if your outcome variable is dichotomous. Um, but he says it should be continuous. I mean, that's probably good advice. If it's dichotomous, you should probably be running logistic regression. Your predictors have to be either continuous or dichotomous, doesn't matter which. As a matter of fact, I shouldn't say dichotomous. I think he says that, but or maybe I added that. They don't have to be dichotomous. They can certainly be some type of other ordinal data or multi-category, categorical. But usually we're going to be dealing with dichotomous, because if they are sort of multi-categorical, we're going to recode them. Non-zero variance, the predictors must not have zero variance. That's sort of a no-brainer. If your predictors have zero variance, there's nowhere to go. I mean, you might as well say the outcome variable needs variance as well. Linearity, we believe, or we argue, the model is in reality linear. And independence. So independence just means that all the values of the outcome should really come from different people or different groups. There shouldn't be dependence between outcomes. Now, that might be frequently violated. For example, we might have one rater rating a whole class. Technically, you could see those ratings as being dependent and that they come from the same rater. You could I mean, to think of it, if you had 2 or 3 different raters, then you get maybe into more of a multi-level or dependence situation. So this is sort of a complicated topic. For right now, I'm going to say we're not going to deal with multi-level modeling. And so we would certainly hope your data is, in fact, independent. Okay, of course, he suggests starting with the provisional analysis, graphing the data, or doing scatter plots, actually a multi-group scatter plot or a multi-scatter plot. And so you can see that here. Now, again, actually, for this first example, we're going to deal with a simple regression. So we're just going to deal with one of these scatter plots. But by looking at the scatter plot, you get an idea of what's going on. Although in real life, it's often hard to look at a scatter plot and know what's going on, even if you're an expert. So again, we're dealing with simple linear regression. With simple linear regression in SPSS, it's pretty straightforward. You just go to your menu at the top, you click or hit Analyze. You'll see the number of options. You hit Regression, and then you hit Linear. Okay, so it's Analyze, Regression, Linear in SPSS. And Field's already done this. So Field does do in the book a model with one predictor. He's predicting album sales from the independent variable, the advertising budget. So the dependent variable is album sales in thousands. The independent variable is the advertising budget. And that's his basic model with one predictor. So we have one dependent variable. Actually, we're never going to deal with the multiple dependent variable situation in this class, but we only have one dependent variable, album sales, and we have one independent variable, which is advertising budget. I should note here, it's important in SPSS to make sure your data has the correct type of scale or level scale. So that's what this is telling you, that this is basically a continuous variable, a scaled variable, and so is advertising budget. So that's what that little ruler is telling you. It's important that you make sure that all your values are set correctly in SPSS. Maybe not so much, well, let's just say it's important. So we have one predictor, dependent variable album sales, independent variable album budget. We then are going to choose our statistics. He likes to pick a lot of them. Regression coefficients, estimates, and confidence intervals, model fit, R-squared change, descriptive, part and partial correlations. These are your semi-partial and partial correlations, collinearity diagnostics, and also case-wise diagnostics to identify any outliers outside 2 standard deviations. So once we put all that in, we would hit continue. And then he also wants to get plots. Remember, he said that he likes to look at the plots of residuals as Y, standardized residuals as Y values, and standardized predicted values as X values. So we look at X predicted as the X value, Y predicted as the, Z residual as the Y value. And we tell it we want to produce all partial plots. We want the histogram, and we want the normal probability plot. Okay, and then we can hit continue again, and it'll continue. And then he wants a lot of diagnostics, which I can understand. And so you can choose a lot of different diagnostics, things you save. And so you can see saving predicted values on standardized, and adjusted, saving standardized residuals, deleted, and studentized, deleted. He's saving a lot of distances here, a lot of influence statistics. He talks about all these in the book. Again, I probably on a regular basis do not use all these. It's good to calculate them. I probably don't use all of them, but we'll be talking about at least some of these as we go along. But so he likes to print out a lot of different, or he likes to create a lot of different diagnostics. Hopefully, at this point, everything's gone well. You entered everything into the appropriate menu boxes. As you went along, you hit continue and everything seemed to go okay. You got back to the main menu and you hit OK to submit your regression analysis. And you look in the output box and you have results. And that's what you want. If you made an error, it's going to tell you error, which is bad. It means you have to go back and figure out what you did wrong. But hopefully you have results, and it should look something like this. Again, this is from Field, and this is a simple regression. So we have a simple one variable model. Although actually, again, we have 2 parameters we're estimating, the constant and the beta weight for the advertising budget. So we're actually estimating 2 things. You can see predictors are constant and advertising budget. The R is 0.578, which would correspond to the correlation between advertising budget and sales. The R squared is 0.335. That's simply R squared. This is sort of strange. It does calculate an adjusted R squared. Most people place very little value in these adjusted R-squares as a indicator of what the cross-validation R-square would be, but SPSS does give it to you. And then it gives you a standard error of estimate, which could be used in setting up confidence intervals around predicted scores. So we're also going to get R and R squared, or we did get R and R squared. And as I said, R is simply the correlation between the observed values of the outcome and the values predicted by the model. R squared is the proportion of variances, accounted for by the model. And adjusted R square is an estimate of the R squared in the population, sometimes called shrinkage. We also get some data on our F statistic, or it's an analysis of variance table actually, which probably looks familiar from when you took analysis of variance first semester. If we look at this printout, we can see that we start with the sum of squares for regression. That's sort of why I think the labeling of field is a little unusual here. Again, he called this SSM, and so there's our sum of squares for SSM. We then get our sum of squares for error, or some people call it residual, and field did label that SSR. And then we get our total sum of squares, and that's SST. Then, of course, we see our degrees of freedom. For regression, the degrees of freedom for the regression is just the number of things we're estimating, which is 2, a constant, and an advertising budget, or the parameters we're estimating. So it's 2 minus 1, which gives us 1. The residual is basically here going to be n minus 2, because it's really going to be the total degrees of freedom minus this regression degree of freedom. Those have to add up. Just you can see the sum of squares add up, and the degrees of freedom are going to add up. So this is going to be 1 plus 198. Our total degrees of freedom is 199, or n minus 1, or the number of subjects minus 1. In this case, subjects, again, are albums. They're not people, but they're still cases or subjects. And so our n is going to be equal to 199. Then we get our mean square, which is just the sum of squares divided by the degrees of freedom. We don't calculate that for the total. We do it for the residual and the regression. And then we get our F value, which is going to be the mean square for regression divided by the mean square for residual, or in his terms, SSM divided by SSR. That gives us 99.587 with 1 and 198 degrees of freedom. And if we go to an F table, that's going to be significant at 0.000, or actually the probability is 0.000. It's going to be significant at 0.05 or 0.01 or whatever you would set as your alpha level to be a little bit more correct. So again, the probability is actually the probability associated with this F is 0.000. And of course, that's going to be significant at 0.05 or 0.001. All right, so returning to Field's example and Field's slides, again, the F statistic tells us whether the variance explained by the model, SSM in this case, is significantly greater than the error within the model, our SSR. And it tells us whether using the regression model is significantly better at predicting values of the outcome than using the mean. So basically, the F statistic, if it's significant, tells us the model works to a certain degree. It's better than random chance in predicting the outcomes. And of course, then we also get our model parameters, or our B's. Now, a lot of people get confused by this. Again, there's 2 kinds of B's. There's little b's and big B's, or unstandardized B's and betas. So some people call these little b's and big B's. Some people call these unstandardized B's, and then big B beta B's. So we have both of those. In this case, again, it's a single predictor, advertising budget, predicting album sales. So we're going to get a constant, which in a sense, it doesn't really matter if the constant's significant or not. In this case, the constant is significant. And what tells us whether its significance is, again, is this t-test that we already discussed. The more important one is advertising budget. For advertising budget, the B is 0.096, and we can see the standard error 0.010. The standardized coefficient, or beta, is 0.578, which should correspond to the correlation coefficient if we go back. The T equals 9.979, and the associated p-value then is 0.000, which would be, of course, significant, either a 0.05 or 0.01 or even 0.001 level. You can see Field also likes to bootstrap the coefficients. The bootstrap coefficient is very similar, as is the, well, it's exactly the same as is the constant and the B weight. And then we get the 95% confidence interval on this. And so you can see the bootstrapped 95% confidence interval around the B weight. Of course, if we look at our model parameters, or our B's in our model, so in terms of interpreting those model parameters, those B values, the unstandardized B values, those represent the change in the outcome associated with the unit change in the predictor. So if we change the predictor 1 unit, how much of a change would there be in the outcome variable? And then the other one we have, of course, is that standardized B value, and they're just that. They're an actual standardized B, standardized beta. So that's the same as basically using z-scores with the constant going through 0. And as we've seen in this simple case, the simple regression case, that beta is going to be the same as the correlation coefficient. Okay, so if we use the model, and here we're using the B's, we can now have a predictive model where we say album sales are equal to the constant, or B sub 0 plus B sub 1 times the advertising budget. So that would be 134.14 plus, in parentheses, 0.096 times the advertising budget. So if our advertising budget is equal to 100, it would be 134.14 plus 0.096 times 100, which would be 143.74 in album sales. Of course, those are both the 100 and the album sales are both sort of adjusted values. We're now going to look at our data set. And we're going to look at a very simple one, one I dropped really later on, but because I said, because of the problem with the, I noted there was a problem in terms of the data, but it's a simple one, and we're predicting deaths from population at the state level. When we do that, we can see we get a very high R, 0.852, which is equal to the correlation between population of the state and total deaths in the state. And the R squared then is going to be 0.725, the adjusted R squared 0.720, and the standard error estimate 3,953.13665, if we want to go out that far. Okay, now if we go to our ANOVA model, we can see here's the sum of squares for regression. Again, these are pretty hard to interpret. Sum of squares for residual, they add up to sum of squares total. Our degrees of freedom for total is going to be n minus 1. We actually had 51 states still because this one includes the District of Columbia. So that the degrees of freedom is 50. The regression uses up 1 degree of freedom, and the residual or error term uses up the other 49 degrees of freedom. We find our mean squares here. You can see our mean squares are really big. We then divide the regression mean square by the residual mean square. It gives us our F value of 129.498. And that's significant. The probability is equal to 0.000. Obviously, it's actually less than that. That would be significant again at the 0.05 or the 0.01 level. Okay, and here we can see then our model. In terms of our model, the thing we're most interested really is the predictor. And of course, the predictor in this case is very significant. Again, we get a t-value of 11.38 for population as a predictor of total deaths. And its significance is 0.000, or its p-value. I should say its p-value is 0.00, which is significant at the 0.05 or the 0.01 level, or even the 0.001 level. The B value for the population is rather low. It's 0.001. Of course, that's because our populations are pretty big. I mean, in some states, we're talking about from 10 to 40 million. And compared to the number of deaths, the B value is going to be relatively small. And it is. The standard error on it is very small. The unstandardized coefficient for the constant is 653.46, but you can see the standard error is larger than the B value for the constant. And in fact, its t-value is 0.885. It's not significant. So in this case, our constant is not different from zero. Our intercept is not different from zero. That's not really a big deal. I mean, usually the intercept isn't of much interest. From a psychological perspective or a predictive perspective. And also in this case, though, we would still, of course, be using that B value to build our predictive model or to make future predictions. And of course, you can see what I did here too is I got the residuals for each state. This sort of tells you what states have done well and what states have done poorly. Of course, larger states are going to have a better chance to do well or poorly. And this is done well or poorly in terms of deaths. In terms of deaths, the states that have done most poorly are New York, New Jersey, Massachusetts, Illinois, and Michigan, and also Louisiana really is up there too. In terms of that have done best, if you want to call best in terms of deaths per population, California, Washington, North Carolina, Virginia, Oregon, Ohio. So that gives you some idea of how the states have done in terms of deaths per population. We're not making any bigger, grander interpretations of this outcome than that, because obviously there's level of analysis issues involved here, but I think it's sort of interesting result. We are now going to look at a second analysis from our data set. This time we're going to look at predicting deaths, COVID deaths, per 100,000 from the density per mile. If you remember from the correlations part of this lecture, density per mile was probably the best predictor. And so we go ahead and run our SPSS analysis with the dependent variable being COVID deaths per 100,000. We're only going to load in one predictor. So it's a really simple model, a simple regression. We're just loading in density per mile. We're just asking for the basic statistics because really, again, with simple regression, we don't need the more complicated statistics unless you want to look at some of the residuals and things like that to check on the assumptions. But so if we look at our basic descriptive statistics, we can see, as we saw before in the correlation segment, there's the means about 91 COVID deaths per 100,000 across the 50 states. The density per mile is about 198 people per square mile. And the correlation between the two, we look at the correlation between the two, so we can look at this table right here. Right here is our correlation. The correlation between the two is 0.545. So the correlation between COVID deaths per 100,000 and density per mile is 0.45. So that's our first piece of output, or first two pieces, really. Our next piece is our model summary. In terms of our model summary, we can see that, as we already knew, our R, or our correlation, is 0.545. And our predictors that we're putting into the equation are the constant and the density per mile. The R squared, which is just R squared, naturally enough, is 0.297. Again, the adjusted R square is pretty meaningless here. And we do have a standard error of estimate, though, that we can use in creating confidence intervals around predicted scores if we wanted to. Although we're probably better off just letting the computer do that. So that's our basic model summary. Next, we have our ANOVA table. So same thing, we're still looking at our dependent variables, COVID deaths per 100,000. Our predictor is the constant and density per mile. As we've seen in other models, we have 50 cases or participants. They're not human subjects, but they're cases. So the total degrees of freedom is n minus 1, or 49. For our model, or the regression model, we use up 1 degree of freedom, and the estimating the error variance, or the residual variance, uses up 48 degrees of freedom. We can see here our sum of squares, which of course add to total sum of squares. Our sum of squares for regression and sum of squares for the error term, or residual. And then we just, to get our mean squares, we divide our sum of squares by the degrees of freedom. You can do that if you would like. And then we divide our regression mean square by our residual mean square to get our F value. You can do that if you'd like by a calculator. And it comes out to 20.295. We could look it up in an F table, but we'll trust the computer value. The computer tells us the probability value associated with that F is approximately 0.000. So again, you don't really say highly significant, but it's darn good significant, or something like that. No, you wouldn't say that either, but it is significant at both the 0.05, the 0.01, and even if you were to adopt the 0.001 level, it would be significant at all those alpha levels. And then this is our final piece of output. Again, we have our regression equation here, and we can, of course, use this regression equation to create a predictive equation. So our regression equation is the constant has a value of 73.197 with a standard error of 6.69. The density per mile has a B value of 0.092. So that means we would multiply the density per mile by 0.092 to get the increase in COVID deaths per 100,000. There is a standard error associated with that of 0.02. We can see our standardized beta coefficient is 0.545, which of course matches our correlation coefficient, which it has to. I mean, the standardized beta is going to be equal to the correlation coefficient in the case of simple regression when we only have one variable. We see the t's associated with each of these variables. The t for the constant is 10.935. It is significant. The t for density per mile is 4.505. It is significant. Again, really the significance of the constant is usually irrelevant to us. And we can get our confidence intervals for our b's, the lower bounds, and the upper bounds. And again, we could create a regression equation. Our regression equation then would be a predicted y for a state is equal to 73.197 plus, in parentheses, 0.092 times the density per mile. And that will give us the predicted deaths per 100,000. Okay, so that brings us to the end. If you have any questions, please direct them to me at dennisdoverspike@gmail.com. I hope this made some sense to you in terms of our discussion of simple regression, especially when combined with all the other resources you have. If not, please bring your questions to our discussion section. Okay, thank you very much. And that is the end for this session.